Sheridan College's Industrial Process Control. This video is part 3 of Lab 5 PID Control, Tuning a Live Process. By now, all the connections and wiring have been set up from part 2. This video will demonstrate the system's response and reaction to changes of proportional integral control and various gains. Follow along while making notes in your workbook to assist you in carrying out the lab for yourself and preparing you for the lab quiz.
Okay, now we've moved from having an open loop response, we're now into live process. We actually have the process operating, maintaining a level in our vessel, our clear plastic vessel. I have right now entered a set point of 50%. What it's showing me here is that my vessel is actually at 27%. And my error is the difference between the two is 23%. I have entered in here also to a gain of 1. I can actually increase the output and probably the height of the process variable by changing that gain to a 2. Now let's see what happens when I do that. What's happened is my process variable has gone up, but I still have this steady state error. Now, no matter what I do, even if I change my set point and I go, say for example, 60, 90, what happens, I still maintain the steady state error. And what you see is this manipulated variable. It's a proportional control, so this manipulated variable has to do with the error times a gain of 2, which gives us a 30% output. Now, in order to take care of this error, to eliminate this error, what I need to do is actually add in an integral. And what you're going to see when I add in the integral is the output of the controller increase until we end up with an error of 0, and then it's going to steady out and maintain a constant rate. So I'm going to put in here, I'm going to go back to an integral of 10. As soon as I hit enter, you see the output of the controller slowly increase, and my error now is decreasing down to 8, 7. It's taking a little bit of time, but what we get is as we approach an error of 0 and our process variable approaches 60, it's taking its time. That's because I have an integral of 10. Down to 1%, giving us, there we are, 60. We're now maintaining an exact measurement of our process variable to the set point. If I make any changes, as an example, I'm going to drop the set point back down to, I'll take it to 40%. 40%. What happens? The output, the controller slows down until my process variable approaches. It's kind of undershot the set point a little, but now it's picking up pace. It's going back up to 30% manipulated variable. I have an error of 0, and my set point process variable is the same. Okay, now what I'm going to do is change this. Put this in 0, so I can eliminate all my integral. I'm going to change my integral to something a lot more, a lot faster, a lot more aggressive. I'm going to change it to a 5, which is actually twice as quick. As soon as I hit enter, what you see is it's quicker now at responding to the steady state error. Now get up, we're almost to 1, we're now at 0, back at 40%. I'm going to change this to 75%, and what you're going to see is a very quick response. A lot of manipulated variable, and it actually overshot and went up to 82. Overshot. And this can be what happens when you have a little too small integral time. I'm going to try that one again, but I'm going to use an integral that's a lot longer. I'm going to go back to the 10. this to 100% and see what happens. See if I overshoot. Notice it goes right up. Well, I've got it at 100%. It's up to the 100%. Just overshoots by a little. It doesn't go way over and above like the other one went to 82 out of 75% process variable. So having a short integral period can allow you a quicker response, but sometimes what would happen is you overshoot. This could be a problem depending on the process itself. Now, I'm going to take this back down to zero integral. Keep my process somewhere around the 50% mark. There we are. You should see what's happened. Our output totally shut off until I get below the set point. Okay, now all I have is proportional in here. I'm going to give this an integral of 1. Let's see what happens when I give it an integral of 1. Notice it's overshot. What we have here is some oscillation that occurs because it's responding too quickly and it doesn't slow down enough. It will eventually level itself out, but if I make any control changes here, I go to 60%, I have, again, another overshoot that occurs. Same thing will happen is if I put in too much gain. I'm going to enter a gain of 10. What you see notice if I enter a gain of 10, what's happening here, it's overcompensating. So it goes over and above the set point, it shuts off, it goes below the set point, turns back on again. And what you have is this oscillation. Now this can cause a lot of problems in your process. It will wear out your final element. Also too, you have an unstable process. If this happened to be a process that was employing a lot of horsepower, like a 400 horsepower pump, what you'd end up doing is shaking your whole building down. It's not good. Your employer will not like that whatsoever. What you want is a nice, quick responding control, one that maintains a nice, steady process. I'm going to take these back to some reasonable tuning. Give this a gain 2. Give this an interval of, I'm going to be kind of in between here and then give it an interval. Now, the last thing I want to show you is I'm going to unplug the transmitter. Now we've learned how each signal, type of signal, has its attributes. The current signal itself, if we interrupt the wiring going to the transmitter, what we want this process to do is completely shut down. So I'm going to pull the wire on the transmitter. As soon as I do that, everything shuts down. The process is completely shut down. It's lost its communication. And if we look at our screen, what we have is a process variable reading very high, 273%, giving us quite a bit of error. But the error is a negative, which tells the process itself, hey, I'm way above where I should be, shut down. And that's one of the nice fail-safe features of using a raised 4 to 20 milliamp signal, current signal, and setting up this type of process control. It has safety to it, and it also too allows us to maintain a nice, smooth, even process. I hope you learned something from this.